So we're going to talk about impulse and momentum. We're going to define what impulse is. And so let's take a look at a real simple situation. Our good old crate on wheels, so there's no friction here. And we're going to apply a force. Are you guys with me? So here's some outside force acting. Some applied force like this. And this has some mass, m. Just keep it really general. Now, this object is going to accelerate, right? And so if I were to draw a free body diagram of this object, this applied force would be the net force, right? You've got a gravity and a normal force, but they're canceling each other out. So this is the only force that isn't canceled out. It's the net force, and it's going to cause an acceleration. And we said that, well, what we originally said was the net force, that this was Newton's second law, was equal to ma. Right? That's what we started with, Newton's second law. Well, then we said, well, let's take a look at this. The net force equals mass, and what is acceleration? It's dv dt. It's the rate at which I change velocity. So it's pretty easy to just take the mass and put it inside that derivative operator and say the net force is equal to the time derivative of mass times velocity. Now, usually we can take the mass out of the derivative and just say, okay, the net force equals ma, because the mass doesn't change with time. But there are situations where the mass does change with time. A jet engine, a rocket engine, the water coming out of a fire hose, that can be quite dangerous. So because you get a force, and that's due to a mass, the rate at which mass is ejected. So in any case, this is how Newton expressed his second law. And we have an expression for mass times velocity, which we talked about last time. We say that momentum, which we use the letter P to represent, because m is taken, is equal to mass times velocity. I mean, this is kind of a definition of momentum right here. This defines what momentum is. And so now we come to Newton's second law, where we say the net force acting on an object is equal to the rate at which momentum changes. Now, the fundamental theorem of calculus, which I think you've all had at some point in your mathematical training, basically says that differential calculus and integral calculus are just inverse operations of each other, the same way multiplication and division are inverse operators. So I can treat this like a fraction. This could be delta p over delta t. And so I'm just going to rearrange this. I'm going to say a little bit of change in momentum is going to be equal to the net force times a little change in time. Okay? In other words, the rules of calculus let me do this. Okay. And now this is a differential, so let's just integrate both sides. Now when I integrate this, when I add up all the little tiny changes in momentum due to my net force, I get the total change in momentum. And this right here is, well, I'm just going to leave it alone, the force, and it has to be the net force times time. Now this right here, when you integrate force times time, when you have a net force multiplied by time, well, that gives you the change in momentum of the object. Force times time is called an impulse. If I apply this force up here, let's say it's 20 newtons, and I apply 20 newtons times 10 seconds, well, that would be 200 newton seconds of impulse. And this is what we're calling it, impulse. And that impulse will be exactly equal to the change in momentum of my object. And this is called the Impulse Momentum Theorem. This little equation right here. Exactly. That's exactly what it means. The question was, if the force is constant, well, I mean, just think about your basic integration rules. If the force is constant, it just comes out of the integral, right? And then the sum of all my little tiny changes in time is just my total change in time, and it just becomes the net force times times delta t. So it becomes a really easy problem. Now this can be interpreted graphically. And by the way, anytime you define a quantity, in this case impulse, through a product, force times time, remember, when you're doing an integration, when you're doing an integral, you're talking about multiplying two quantities together. Right? It's just this stuff times this stuff. But the reason you have to use all those tricky math, calculus tricks is because this stuff sometimes depends on this stuff. Unless it doesn't, if it's a constant, it just comes out of the integral and you just are multiplying 2 times 3 or something. Okay, it becomes easy. Well, anytime you have a quantity like impulse, or I'm sorry, force times time, and by the way, this really has to be the net force for this to work. Maybe you have a force that's a function of time. Well, that means the area underneath this graph represents my change in momentum. This is a really handy little diagram to try to understand. Force times time. The area underneath a force versus time graph gives you the impulse to the object. And remember, this has to be, I'll go ahead and put it, net force. And so, of course, this allows you to solve all kinds of problems. Let's talk about change in momentum. Well, that's P final minus P initial, right? So this is going to be m1 v1. Let's say you have, I'm sorry, I'm getting ahead of myself. Let's say the mass is constant. This would allow you to say the mass times the final velocity minus the mass times the initial velocity will be equal to whatever, f dt, whatever this turns out to be, and it allows you to solve for a final velocity fairly easily. And so I think, but anyway, this is the impulse momentum theorem right here. And what we need to do now is we need to work some example problems where we practice using this idea. So that's what we're going to do now.